Hi everybody, welcome to lecture 2 of Electrical Engineering 331. We will in this lecture continue to talk about signals, and in particular today we'll talk about periodic signals, and we will begin to talk about aperiodic or non-periodic signals as well. So let's jump right in, and this is section 1.3 in your book. Function is said to be an even function of t if x of negative t is equal to x of t for all values of t. And so an example of this is x of t equals cosine of t, because we know that cosine of negative t is the same thing as cosine of t. So that means that cosine of t is an even function of t. Similarly, if we look at the function t squared, that is also an even function of t, because if we took the quantity negative t, the quantity squared, in other words, we squared everything there, we squared the negative sign and the t, or another way to think of it is if we plugged in negative t for t in here, then when we squared that, the negative sign would get squared as well, and so we would arrive back at t squared. So what that means is that if x of t is equal to t squared, then x of t is also an even function of t. And as the next sentence notes, even functions have graphs that are symmetric about the vertical axis. So here you see cosine of t, and you can see how this looks just the same to the right. It looks as though you flipped it over to get the left-hand side, and similar for t squared as well. So these have even symmetry about the vertical axis, and they're said to be even functions of t. Now, a function is said to be an odd function of t if x of negative t is equal to negative x of t. Again, remember up here, for an even function, x of negative t is equal to positive x of t, but for an odd function, x of negative t is negative x of t. And that must be true for all t in order for it to be considered to be an odd function. And we have examples of odd functions as well, easy examples of odd functions. For instance, x of t is equal to sine t is an odd function because sine of negative t is the negative sine of t. And similarly, x of t is equal to t cubed is an odd function of t, because if we substituted in negative t here for t, okay, the negative sign would get cubed, which would give us a negative sign, and then we'd have negative t cubed, which would be the negative of x of t. So that means that x of negative t is negative x of t, which means in turn that x of t is an odd function. And odd functions have graphs that are anti-symmetric about the vertical axis. And what that means is that if you took what you have to the right of the vertical axis and flipped it about the axis, then you would need to then flip it once more about the horizontal axis, and that's called anti-symmetry. And you can see how that's true here for the sine of t, and it's also true for t cubed. Imagine you flip that about the vertical axis, and then if you flipped it again about the horizontal axis, you would get this part. So that's called anti-symmetry, and anti-symmetry about the vertical axis, and that is characteristic of odd functions. Now, an interesting thing is that most functions that we encounter are neither even nor odd. But there is something interesting that you can do with any function. Okay, so let's say that x of t now is any function, and it's not necessarily even or odd, it's just an arbitrary function. Well, if we define a function x of e of t, which is equal to 1/2 x of t plus 1/2 x of negative t, that is even. Can you see that it's even? Because you remember, this is going to be even if xe of negative t is equal to xe of t. And let's check that down here. Xe of negative t, okay, using this definition here, that would be 1/2 x of negative t, because again, we're just plugging in negative t for t into this definition. So we'd have 1/2 x of negative t plus 1/2 x of negative t. But that's the same thing as 1/2 x of negative t plus 1/2 x of t, which is just the same as xe of t. So indeed, xe of t is an even function, because we've just proven that xe of negative t is equal to xe of t. And in a similar fashion, if we define xo of t to be 1/2 x of t minus 1/2 x of negative t, well, that will be odd. And we can prove that as well, because if we take xo of negative t, okay, stick in negative t everywhere here for t, and we would have 1/2 x of negative t minus 1/2 x of the negative of t, and so that would be 1/2 x of negative t minus 1/2 x of t, which is exactly the negative of this xo of t. So we've just proven then that xo of negative t is negative xo of t, which is that's the defining characteristic of an odd function. So xe of t is an even function derived completely from x of t, and xo of t is an odd function derived completely from x of t. And now for the most interesting part. If you add xe of t and xo of t together, you see you would have, okay, xe of t is 1/2 x of t plus 1/2 x of negative t, and xo of t is 1/2 x of t minus 1/2 x of negative t. So when we add it all up together, we get x of t. So in other words, x of t is exactly equal to xe of t plus xo of t. That means that this is a decomposition of x of t into even and odd parts. So even though the general function that we would encounter, I'm thinking of x of t here as being a general function, even though the general function that we would encounter would be neither even nor odd, we can always decompose any function into even and odd parts. So let's see how that would actually go in one example. Okay, so here is a function x of t. And it's clear that that is neither even nor odd, because it is neither symmetric nor anti-symmetric about the vertical axis. So this x of t is neither even nor odd. But we can decompose it into even and odd parts as follows. Now, if we want to get xe of t and xo of t for this function, remember, again, xe of t is 1/2 x of t plus 1/2 x of negative t, and xo of t is 1/2 x of t minus 1/2 x of negative t. Well, we notice that both of those expressions contain x of negative t. So if we're going to find xe of t and xo of t from x of t, we better find x of negative t as well. And so that's the first step. We start with x of t. Our first step is to find x of negative t, and it looks like this. And then to get xe of t, we just take 1/2 of the graph on the left plus 1/2 of the graph on the right, and here's our function. Here's our graph of xe of t. And on the other hand, to get xo of t, we take 1/2 of the function on the left minus 1/2 of the function on the right. and we get this. And I think you can notice easily that, you can just see from the picture, xe of t is indeed an even function of t because it's symmetric about the vertical axis, and xo of t is indeed an odd function of t because it is antisymmetric about the vertical axis. And furthermore, I think you can also see that if you add these two functions together, you will recover your original function, x of t. So this is an example showing the decomposition of an arbitrary function into its even and odd parts. Okay? So now we'll begin to talk about periodic functions. A function x of t is said to be periodic if there is some number t naught such that x of t plus nt naught is equal to x of t for all t and also for all integer values of n. Now, I put over here in red a remark. T here is taken to be a positive number. And keep in mind, that means it's not a negative number, and it also means it's not zero. It is actually a positive number, okay? If you cannot find, this should be T naught here. Okay, this should be T naught. Actually, just for the sake of completeness, I'll correct that. Give me just a moment. Okay, that will be corrected shortly. It takes a moment for this to sync. Oh, let's see. There we go. Okay, so now you see it's T naught here. Okay, but resuming what we're saying then, if there is no such T naught, if you cannot find any positive value T naught such that this is satisfied, then the function is not periodic. And so it's called either an aperiodic or a non-periodic function. But if there is some positive T naught such that x of t plus nt naught is equal to x of t for all values of t and for all integer values of n, then x of t is said to be a periodic function. And t naught is called a period of the function. So let's look at an example of this. If we consider x of t is equal to cosine of 2 pi t, 1 is a period of that. And we can prove that as follows. Okay, x of t plus nt is equal to cosine of 2 pi times t plus nt. And so that's cosine of 2 pi little t plus 2 pi n times big T. And remember now we're looking at capital T equals 1. So that ends up being cosine of 2 pi times little t plus 2 pi n times 1, which is the same thing as cosine of 2 pi t plus 2 pi n, where n is any integer, remember. And now if we use the cosine over sum formula, remember that says that the cosine of a plus b is cosine a cosine b minus sine A sine B. So here we have cosine of 2 pi t, cosine of 2 pi n, minus sine of 2 pi t, sine of 2 pi n. Well, you might remember from your trigonometry that the sine of any integer multiple of 2 pi is 0, and the cosine of any integer multiple of 2 pi is 1. So we have cosine of 2 pi t times 1 minus sine of 2 pi t times 0. So we're left with cosine of 2 pi t, which of course is just equal to x of t. So we have proven that x of t plus nt, x of little t plus n times capital T is equal to x of little t, and therefore x is a periodic function. Now, an interesting point here is that if you had tried capital T equals 2, or capital T equals 3, or capital T equals 4, they would have also worked. They are also periods of this function. And so we summarize that right here in this paragraph. We say, note that if capital T is a period of x of t, then so are 2t, 3t, and any other integer multiple of capital T. So what we do then to resolve that sort of ambiguity is we let t naught be the smallest positive value of t that satisfies x of t plus nt is equal to x of little t plus n times capital T is equal to x of little t for all little t and all integer values of n. And then t naught, that smallest value of capital T that works, is called the fundamental period of x of t. And so up here, 1 actually is the fundamental period of cosine of 2 pi t. You can try it if you want, but you'll see you cannot find any smaller value of capital T that would always satisfy the equation x of little t plus n capital T is equal to x of little t. But larger values such as 2 or 3 or 4 or 5 would work. Okay? So t naught, this 1 here is the fundamental period. It is the value of t naught in that case. And we look now at a couple of other cases. If x of t is equal to sine t, then t naught is 2 pi. If x of t is equal to sine squared t, t naught is equal to 1 times pi. And you can see that most easily from the graph here. Here's a drawing of sine of t. And you need to be careful when you're looking for the period. If you only looked at where the function crosses the axis, you might be tempted to think that the period of this function is pi, because it does repeat. If you're looking just at those points, it repeats itself every time t increases by pi. But if you look away, you'll see that pi is certainly not the period, because if you take this point here at the peak and you increase by pi, now you're at a trough. So actually the period is 2 pi. To go from peak to peak, you go 2 pi, or to go from trough to trough, you go 2 pi. So the fundamental period of sine of t is 2 pi. However, sine squared of t, when we square this function, all those negative portions come up above the axis, and so sine squared of t looks like this. Now that graph is not a perfect graph, because actually we shouldn't have these sharp corners. In fact, let me fix that graph, because that's really not quite right. I mean, the basic character of it is correct, but we shouldn't have those sharp corners. So let me change that. Give me just a second here. I hope this won't mess up the whole graph. No, it's not too bad. Okay, so it's going to be, oops. Okay, and once again, we're going to have to see if we can get this to sync. There we go. So you see, this is how we ought to draw that. It does go to 0 at 3 pi, 2 pi, excuse me, at negative 3 pi, negative 2 pi, negative pi, 0 pi, 2 pi, 3 pi. It does go to 0 just as the previous graph, but we shouldn't have those sharp corners. These are, it's a rounded curve, okay? And so you can see though that because the negative portions of this graph have now flipped up above the axis, we now have a situation like this, and that means that the period is actually just now, the fundamental period is just pi rather than 2 pi. So that's how we that's one way to find the period, the fundamental period of a function. Okay, so now the last portion of lecture 2 is an introduction to non-periodic functions. These are also called aperiodic functions. And we're just going to get started on this. We won't be able to finish it completely, but we're going to begin our discussion of non-periodic functions by looking at two particular non-periodic functions that can play a pretty big role in this course, and they also have some convenient features. So let's look at them. The first non-periodic function we want to consider is called the unit step function. And the unit step function is usually designated u of t, and is equal to 0 when t is less than 0, and it's equal to 1 when t is greater than 0. So here is a graph of the unit step function. And that's about all there is to it. Now, you might wonder, well, what does u of little t minus capital T look like? Well, we're going to do this in exactly the way that we learned last time. We just substitute little t minus capital T in this definition everywhere we see t. So we have u of little t minus capital T on the left, and on the right we have 0 and 1, but now instead of saying for t less than 0, we say t minus capital T less than 0 and t minus capital T greater than 0. And remember then, to finish this up, what we want to do is to have these parts of the domain, these restrictions expressed in terms of t, not in terms of t minus capital T, and we can easily get that by just adding capital T to each side of this, these two inequalities. And so we get finally this expression right here, u of little t minus capital T is equal to 0 for little t less than big T, and it's equal to 1 for little t greater than big T. So it looks like this. So the effect of adding in that negative capital T in the argument has just been to shift the function to the right by the amount capital T. And another unit another aperiodic function that we consider is called the unit ramp function. And it is typically given the symbol r of t, and it's equal to 0 for t less than or equal to 0. But for t greater than or equal to 0, it's equal to t. So it ramps up. And similarly, if we wanted to know what r of t minus capital T looks like, we just substitute t minus capital T everywhere here that we see little t. And so we have r of little t minus capital T is equal to 0, and then this t becomes t minus capital T, this t becomes t minus capital T, this t becomes t minus capital T. And then in these inequalities, we just add capital T to each side, and we get this equation down here. And so that's just like we got above with the unit step function. When we put the negative t in the argument, it just shifted the step to the right. Well, here, adding negative t to the argument will just shift the ramp to the right. Actually, I see now I probably should have graphed r of t, so let me once more make a little change here. So let's see here. See, this is what the unit ramp function looks like. As I said, it just ramps up. Since this equal to t, when t is greater than or equal to 0, it's just a line of slope 1 beginning at t equals 0. And here now this has completed, and so we have a line of slope 1 here as well, but it begins at t minus capital T, rather than at 0. Now, these functions, we're going to find out these functions are useful in several different ways, but let me show you just one simple way in which they're useful, one way we can understand already. So, those of you who came to the last Zoom meeting will possibly remember, and if you don't remember it, you can look at the recording of the Zoom meeting. And by the way, I'll go ahead and announce now that, or remind you that the recordings of the Zoom meetings are in the Panopto section of Blackboard. So anyway, in our last Zoom meeting, near the end of the meeting, one student was asking about getting more practice in trying to find the expression for a function from the graph. And so I tried to give a rather difficult graph, and I showed how to find the expression for that graph, and the answer. Now keep in mind, again, this was something I made up on the fly during the meeting in response to a question. This graph is not in the lecture video. It is in the Zoom video, but it's not in the lecture video. But anyway, using the method that we discussed in lecture video 1, we came up with this answer as the expression for this function. And we checked it and were convinced that it was correct. But now I want to show you that if you're very careful, you can use these functions u of t and r of t to come up with the same answer in a different way. So let me show you how this would go. Now, this is going to take some practice, so don't be frustrated if at first this seems a little bit mysterious, because we'll look at other examples as well. But how would we write this in terms of these functions u of t and r of t? Okay, well, let me just go ahead and say the answer is this. We have x of t is equal to 14 u of t minus 5r of t plus 5r of t minus 2 plus 6r of t minus 2 minus 6r t minus 3 minus 10r t minus 5 plus 10r t minus 6. Now, I'm sure that's probably a little confusing to you, but notice how neat and compact that expression is. So I think that that's a motivation, to be able to write this function that compactly. That's a pretty attractive idea, and so that helps to motivate you to understand, well, why is this correct? So let's look at the graph now, and I'll show you piece by piece how I got this. So when we're doing this, we go from left to right. Now, in the graph, the graph is not shown to the left of 0, but it's assumed here that over here the function is 0. In fact, maybe, let's see, I don't really recall. Oh, wait, here we go. If we look at what we did at the end of the period, yeah, we showed a little bit more. This is the example that we did in the Zoom period, and here we show the function being 0 over here to the left. So so just take this function here. Let's see if I might be able to do this. Let's see. There. So we're going to take that function to be 0 everywhere to the left of 0, but to the right of 0, it is as shown here. So how do we write down the expression for this? Well, the first thing we see is that at 0, we have a sudden jump. We jump up by 14 units at t equals 0. That's how we get 14 u of t. Because the u of t, it's a jump. This is a jump by 1, but we want to jump by 14, so we have to say 14 u of t. And we don't have u of t minus 1 or t minus 2 or anything like that, because this is t minus 0. It happens, the jump happens right here at 0, so it's just u of t. So 14 u of t. That takes care of the jump. That puts us up here at 14. Now, the only other thing that's happening here at t equals 0 is we see we see the beginning of a ramp going down. And all we have to do is figure out what the slope of this ramp is. And again, this is rise over run. We see that this is, here's the point 0.14, here's the point 0.24. So it goes down, it has a vertical change of -10 and a horizontal change of 2. So -10 divided by 2 is -5. So that's where we get the -5r of t. And again, that ramp starts right here at 0, so that's why it's r of t and not r of t minus 1 or t minus 2, anything like that. So these first two terms are giving us the start up here at 14 and the ramping down. And if that's all we had, this would just keep on ramping down forever and ever. But that's not what we want this to do. We want it all of a sudden here to change at t equals 2. Now, the way that I like to do this is I think of it as follows. Okay, we have this, the -5r of t is what's making this go down. So the first thing I'd like to do is to flatten that out, to undo the downward slope. And the way to do that is just to add in, since I have a -5 ramp, I'd have to have a +5 ramp. But this one starts not at 0, but at 2. So it's +5r of t minus 2. Now what that will do is that flattens this out. So if all I had was 14u of t minus 5r of t plus 5r of t minus 2, I would just have a graph that would come down like this and then would flatten out. But that's not all I want it to do. I don't want to just flatten out. I want to actually then go up. Now, what is the slope here? Well, the rise, we're going from 2.4 to 3.10. So the rise is 10 minus 4. The rise is 6 over a horizontal distance of 3 minus 2 is 1. So 6 divided by 1 is 6. So we have to add in this 5r of t minus 2 is to flatten out this downward ramp, and then we have to add in another 6r of t minus 2 to give us this upward ramp there. So that's where we get this next term, 6r of t minus 2. And then once we get to t equals 3, we want to flatten it out. And just like we talked about the flattening before, since we have a upward 6r here, we just need a negative 6r starting at 3 to flatten it out. So that's minus 6r of t minus 3. That will continue on until t equals 5, and then we want it to ramp down very sharply. Let's see what this slope is. It goes from 5, 10 to 6, 0. So it goes 0 minus 10. The vertical change is negative 10. The horizontal change is 1. So the slope here is negative 10. So we have a negative 10r, a ramp that has negative 10 magnitude. And where does it begin? It begins at 5. So that's why this is r of t minus 5. And if that was the last term, this would just keep going down to forever, but we don't want that to happen. We want it to flatten out, and so we have to add in a 10r beginning at 6 to flatten it out. And I claim that that will give us this graph. Now, let's see if that works out. Well, if this is true, then x of t is equal to the following. When we look in the region t is less than 0, all of these expressions are equal to 0 when t is less than 0. So we would just get 0. Now, if we look for t between 0 and 2, okay, this term has turned on. Once we get past 0, this term has turned on, so that gives us the 14. And this term also has turned on because it begins at t equals 0. So once we get past 0, it's turned on. And so we have minus 5 t. Remember, once the ramp turns on, it's equal to t. So we have minus 5t. But this one has not turned on yet because it doesn't turn on until we get to t equals 2. So between 0 and 2, we just have those two terms, 14 minus 5t. Now, once we go to a value of t between 2 and 3, okay, those two terms from above are still there, 14 minus 5t. They're still valid, but now that we've gotten between 2 and 3, now the 5r of t minus 2 and the 6r of t minus 2, those both turn on. So we have to put that down here. We have 5 times t minus 2, that's the 5r of t minus 2, 5 times t minus 2 plus 6 times t minus 2. That represents the 6r of t minus 2. Now as we go to the next region for t between 3 and 5, okay, everything that was on here is still on, so we have 14 minus 5t, 5 times t minus 2, 6 times t minus 2, but once we move to the region between 3 and 5, now this will turn on. And so we have to put in 6 times t minus 3. And minus 6 times t minus 3. And then we move to the next region, and everything again, we bring down everything from before, but now that we go between 5 and 6, this turn on. So now we have minus 10 t minus 5. And finally, once we get past 6, everything is turned on, and so we'll add in this last term. And now let's see if it all works out correctly. Okay, the 0 is 0, 14 minus 5t is 14 minus 5t. Then let's see, 14 minus 5t plus 5t, so the t's go away. And we have 14, and 5 times negative 2 is negative 10, so 14 minus 10 is 4, and 4 minus 12 is negative 8. And we have a 6t here, so 6t minus 8 right here. And let's see if all of this, if all of this is equal to 6t minus 8, well, that's identical to this part right here. So we would have 6t minus 8 minus 6t. So we're just left with minus 8 plus 18. So we have 10 in that region. 10. And then notice that this is identical to this. So this is 10 minus 10t plus 50. So that 10 minus 10t plus 50 is 60 minus 10t. So we have this in the region for t between 5 and 6. And then if all of this is 60 minus 10t, and then we have 10t minus 60 added to it, then we have 0. So this, after you do all the simplification, this is the expression that we have. And lo and behold, you'll see that that exactly matches what we had last time in the Zoom session. So I hope that this convinces you that these these are called singularity functions. We'll talk a little bit more about the reason for that next time. But U of t and R of t are called singularity functions. They're not the only singularity functions, but they are two that we will use a good bit in this course, and you can see how useful they can be. They give you a very compact way of expressing a function as long as you're careful about what you're doing. So to finish this lecture, let's look at one more example of using singularity functions to express a function, and then that will be it for this lecture. So as example 2 here, this is actually the function from example 2 in our first lecture video. So we had this graph, and again, just as before, this graph is taken to be 0 over here in the region t is less than 0. And we wanted to find the expression for this function. And using the methods of lecture 1, we found this expression right here. This is x of t. But now we want to use, instead of using this approach like we did in lecture 1, let's try using the singularity functions. So let's think about it. As we move from left to right, what's the first thing you notice? The first thing you notice is a ramp going up. There's no jump this time like there was in the previous example. There's just a smooth transition, because remember, we're supposed to have 0 over here. Let me actually write that in. Okay, so we have 0 over there. And then we have this smooth transition, so there's no jump, there's no u of t, but we do have a ramp up, and the slope of that, it rises by 2 units in a horizontal distance of 1, so we just 2r of t. So we have 2r of t, then we want that to flatten out starting at t equals 1, so I'm going to say minus 2r of t minus 1. And then I have another slope here. Let's see, what is this slope? We go from 2 to 6. So we have an increase of 4 and a distance of 1. So we have 4. We have a 4r, but we want that to start at 2. So that's 4r of t minus 2. And then to flatten out that 4r of t minus 2, we'll have to say minus 4r of t minus 3. And that will flatten it out. And that's all we should have. So let me now go over with you so that you can watch. So there's the 2r of t to give you this upward ramp of 2. Then the minus 2r of t minus 1 to flatten that out. Then a 4r of t minus 2 to give you this new line of slope 4 starting at 2. And then a minus 4r of t minus 3 to make that flatten out starting at t equals 3. And we can finally now check this to make sure it works out correctly. And so let's see, we'll do this just as we did before. Okay, x of t, if t is less than or equal to 0, all those functions are equal to 0. So x of t is equal to 0 if t is less than or equal to 0. Now, as we, and we're going to turn these on one term at a time, just as we did before. So when t gets between 0 and 1, all these terms will still be turned off, but the first one will turn on. So we have 2 times, and remember r of t is t, so 2t when t is between 0 and 1. Then as we continue to increase t and it gets between 1 and 2, okay, that 2t will still be on, so we bring it down. But now, once we get past 1, this term will turn on. So we have minus 2 times t minus 1. And then once we get past 2, okay, these 2 terms are still on, but then this term will turn on. So we have plus 4 t minus 2. And then finally, once we get past 3, we will have to add in this minus 4 t minus 3. And so let's see if this all works out. We have 0, 2t. Okay, here we have 2t minus 2t is 0. Minus 2 times minus 1 is 2. And so now if this is equal to 2, remember that's what we have right there. So we have 2 plus 4t minus 4 times 2 is 8. So that's 4t minus 8 plus 2 is 4t minus 6. Right there. And then if all of this is equal to 4t minus 6, then we have minus 4t. That gets rid of all the t's. And then we have minus 4 times minus 3 is 12. But we had 4t minus 6. So the minus 6 and positive 12. just gives us 6. So this is what we ended up with. And if you compare that to what we had in our first lecture video, you see that it is exactly the same. So I hope that this really convinces you that these singularity functions are worth becoming familiar with. Already we're seeing that they seem to offer some advantages, and as I said, we will use them really quite a bit in our later work in this course. So that concludes lecture 2, and I'll talk to you soon.